Now let's talk about our last topic, finding the prime factorization and least common multiples. So think back to our discussion on multiples earlier. The multiples were a product of some value n times one of the counting numbers. Similar, we can think to our examples here. So for example, the product 72 is comprised of a couple of factors. A product of two counting numbers 8 times 9. Now there are multiple ways to actually multiply two values together to get 72, but this is just one example. So we say that 8 and 9 are the factors of the product 72, much in the same way that if I have a peanut butter and jelly sandwich, it's comprised of one part jelly and bread and another part peanut butter and bread. Multiplying them together gives me a delicious sandwich. So there's one other thing we can think about with regard to factorization, and it's this idea that we can split most numbers, I say most, all numbers into two categories. They're either prime or composite. A prime number is a counting number greater than 1 and only has factors of 1 and itself. So for instance, in my list here, you can see that 2, 3, 5, and 7 are the prime numbers, meaning that the only way to make them through a product is by multiplying themselves by 1. The other numbers here are composite numbers, meaning they're composed of numbers other than 1 and itself. Now they do have factors that could be 1 and themselves, but those are not the only factors. So for instance, from my list here, those would be 4, 6, 8, 9, and 10. And you can see the different factors that they're composed of. So what is prime factorization? Prime factorization is figuring out what a composite number breaks down into with regard to the prime numbers, right? So the prime factorization of a number is just simply the product of all the prime numbers that equal up to whatever our current value would be. So how do we actually perform that operation? Well, find two factors whose product is the given number, and then start by creating two branches. If a factor is prime, then the branch is done. If not, then we continue the process again and break these down further. So as we build out our tree, you'll see the branches that end in prime numbers being complete. And at the end, the prime factorization of a number is just multiplying all of those prime values together. So let's look at a specific example to get an idea. So ask yourself here how to find the prime factorization of 48. This actually harkens back to our discussion on divisibility rules. There's actually multiple ways that I can multiply two values together to get 48, right? So the question here is, where do I start? Well, it's sort of up to you. So let's start from the beginning here. Our branch is going to begin with 48, and all I want to do simply is figure out what are some values that I can multiply together to get 48. And this depends on the divisibility rules that we talked about earlier. So our last digit here is actually an even number, 8. That means that 2 is actually a really good value to choose. And the question is, 2 times what number gets me to 48? Well, the answer is 24 here. So of the two values, 24 and 2, I could say that 2 is a prime number because the only factors that I can come up with that multiply together to give me 2 are 1 and itself. So I can't say that about 24, which means our branch is not yet concluded. So I'll sort of underline this value for now and then continue on with our other branch. So think about 24. Again, we could say the same thing. This is also divisible by 2. 2 times what gets me 24? Well, this time I could say it's 2 times 12, where prime number 2 is underlined and our branch continues on the other side. Breaking down 12, what are the factors that I could come up with to say what are going to be those values? Let's pick something like 3 times 4. Now, in this case, 3 is the prime number, and 4 is another composite that we could break down further. So what times what gets me to 4? Well, 1 times 4 doesn't really help us, although that is a true factor. We're looking for the prime values here, so we break down 4 into 2 times 2. And we've completed the tree. Now if you'll notice, all the underlined values are prime numbers, And they're basically going to be multiplied together to create the prime factorization of our original value. So my first digit is going to be 3 times 2 times another 2 times 2 again, and our last one, right? So this is the prime factorization of 48. And this is what we talk about in terms of how do we manipulate larger values? How do we perform operations on these larger values? Looking at the underlying structure of how they're composed of different prime numbers really is helpful. And this will make a little bit more sense when we talk about fractions, as well as multiplication and division in some later topics. So for now, let's look at another example. If I ask you to find the prime factorization of 60, you can repeat the process in a similar manner. So as I said a second ago, there's actually multiple ways to get factors of our original expressions. As we saw earlier, for 48, we could have divided by 2, but 4 plus 8 actually equals 12, which is a number divisible by 3. So we could have actually divided by 3 to begin with. So why don't we start there in this case? 60 is actually another number where the sum of the digits is divisible by 3. We get 6 plus 0 is 6. 6 is divisible by 3. So what can we multiply by 3 to get 60? Well, the answer is 20. So in this case, 3 happens to be my prime value, and 20 now I could break down into further numbers. So 20 I could actually break down into 2 times, let's say, 10. And 2 happens to be the prime number here. Repeating the process one more time, I get 10 breaking down into 2 times 5, both prime numbers. And so finally, I can wrap up and say, collecting my prime numbers, the prime factorization here of 60 is 2 times 2 times 5 times 3. And there we have it. Now our next topic is the least common multiple. Now recall that a multiple is just some value n multiplied by one of our counting numbers. Now the least common multiple is just the smallest number that two multiple of both numbers have in common. So let me give you a visual example to explain. Imagine that the length of the arrows here are, let's say, 10 and 20 inches. Now, as I look at the figure here, imagine that these are two wheels with diameters of 10 and 20 inches. If I were to roll these, the arrows would sort of follow the following pattern. So as I roll this value, it hits here, and it sort of has this pattern like this, and it moves along. So the distance from the starting point and the touchdown would be 20. And if I move out to the next one, the distance from the starting point to this arrow here would be another 20. So let's add it together and say that's 40. And the starting point again to the third distance would be another 20, so 60 in total. I can repeat this process for the smaller wheel as well. When it first rolls, it'll hit about midway here. Rolling again, touches down at the midway here.